fast. Now, if we want to take another example, which is 20.375, and we want to change it to octal. Basically, we have to change to decimal and then the octal. However, we have to divide it over 8 this time because it's an octal. So 20 over 8 is equal to 2 plus the remainder 4, and the remainder 4 is placed exactly next to the decimal point. We take 2, do it the same, and we have the remainder 2. However, for the value that is to the right of the decimal point, we take them and multiply it by 8, and we get 3.2. We take the 3 and place it next to the dot, and we have 2.2 and multiply by 8 again. We get 1.6. We place the 1 next to the 3, and so on. And then we take the 0.6 and multiply it again by 8. We get 4.8. We take the 4 and place it next, and we can continue. However, we are going to stop here for 3 decimal values, so we get 0.314. Now, do we have a fast conversion, or should we always multiply and divide? Yes, we do have a fast conversion. If we want to convert octal to binary or hexadecimal to binary, then we have a very nice and fast conversion. Each octal digit can be represented by 3 digits in binary. So for instance, 5, it means 101. However, for the hexadecimal, each digit in hexadecimal can be represented by 4 digits in binary. So for instance, 7 means 0111, and 9 means 1001. For instance, if we want to convert 352 in the octal numeric system to a binary, we take 1 digit at a time. The 3 represented by 011, the 5 is represented by 101, the 2 is represented by 010. And concatenating all these together, we get 0111, 01010 to the binary numeric system. And the same thing if we want to convert the hexadecimal value, which is 2A3, convert it to binary. We do it the same. We take the 3 and convert it to binary value, and we get 0011. The same thing for the next digit, which is A, which means 10, and we convert it into binary 1010, and the 2 is 0010. You know that those zeros to the left does not mean much, so we can remove them. And we end up with this value 10101000011 in the binary. Now, I'm not asking you to memorize this, but actually you can easily find those values, and this helps you to convert from hexadecimal to binary and from binary to hexadecimal. For instance, 4, it means 0100, and 7, 0111. However, the first from 0 to 7, we need them from octal to binary, because the 7 is the highest number in the octal numeric system, while the remainder from 8 to F represents 15, which is 1111, are used for hexadecimal. Again, the octal is 3 digits and the hexadecimal is 4 digits. This can be very easily, found or calculated through this small table. let's assume the first digit, or let's have the first digit as 1, the second is 2, the third is 4, the fourth is 8, and the fifth is 16, and so on. And the one that follows the 32. But however, let's assume that we want to find what does 9 represent in binary very quickly. 9 is basically 1 and in the position of 8, and it needs another 1 in the position of 1, and 8 plus 1 is equal to 9, and we fill up the remaining boxes with 0. So 9 is 1 0 0 1. This is a fast way. Okay, there's another system which is called BCD. BCD stands for binary coded decimal. It is a way where decimal digits are represented by binary very quickly. Instead of dividing by 2, we just have each digit to be represented by 4 binary digits. Let's have, for example, 7. It's represented by 0 1 1 1. You have to have 4 digits. Example, let's say that we have 563 and we want to convert it into BCD. We take one digit at a time. The 3 is basically 0 0 1 1. Again, each digit is 4 digits in binary. 6 is 0 1 1 0, and 5 is 0 1 0 1. We concatenate these together and we end up with a long BCD number. However, you have to be careful that BCD is different than binary. The value of 563 in binary looks like this, but in BCD it looks like this. However, if you have to put BCD, otherwise people might be mistaken. ASCII code is another representation to characters. Each character on your English keyboard, for instance, is represented by a value. This value is a 7-bit value. We add to it another bit. This bit is called parity check, so as to make it into 8 bits, because we have, so it could be called as byte. So for instance, A, the letter A is 1011111. It's 95, most probably. It's top of my head. If we want to add a parity check, let's say we want to add an even parity check to this value. The even parity check, if we want to find out like 95 what does mean, here's another way of getting the value very quickly. We put 95 in the calculator of the Microsoft, and then we change it to binary. We get the 1 0 and then 5 1s. All what we need, just copy it and paste it here. Now, talking about the parity check, we have to count the number of ones in this. If we want to use even parity checks, it means that the number of ones must be even. So if we want to count the number of ones in this 95 value, we have 1 2 3 4 5 6. So it's 6 ones. So it's basically 6. Basically, it's an even number. All what we need to do now is to put the value 0 to the leftmost bit, which is called the parity check bit. However, if the number of ones is odd, we have to put 1 in order to make the number of ones even. Talking about the complements, remember we have n-1 complement, which in terms of binary, it is where n is equal to 2, we are referring to 1's complement. So with the 1's complement of, for example, this one, 10110, means all what we need to do, just put the all ones on top of it and subtract. So 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is another 0, and 1 minus 0 is 1, and so on. So it's basically equal 1111 minus the value. Or it is the opposite of the value. So if it is 0, then it is 1. If it is 1, then it is 0. This is a fast way of finding the ones complement. For example, in the decimal numeric system, where we have n equal to 10, we're talking about the 9's complement. We do the same thing. 9's complement of 675 is equal to 999 minus 675, which gets to 324. On the other hand, the n's complement, which if we are talking about in the binary system, we are talking about the 2's complement, since n is equal to 2. So the 2's complement is basically the 1's complement plus 1. The 1's complement of this one is the opposite of this one, which is 1, 0, 0, 1, 0. Plus 1, we add 1 to the 1, we get 2. So it is 0, 1, 0, 1, 0. In the decimal system, we have n equal to 10. For instance, 10's complement of 763, it is the 9's complement plus 1. The 9's complement is 236, plus 1, we come out to 237. Talk about the signed numbers. All what we need to do is just add a bit to represent the sign in the most significant place. So for instance, in the 5-bit code, we add 0 in the position in the last bit if the value is positive, and we add 1 or we make it 1 if it is negative. This is called signed bit or the sign. For signed two complements, let's say that we want to have the value of minus 7. Minus, we put in the signed bit position 1, and the remainder is the 2's complement of the value 7. The 7 is equal to 0, 1, 1, 1, and the 2's complement is 1, 0, 0, 1. However, if we are talking about 6-bit code, then it is the 2's complement if we are referring to the 6-bit code, which is equal to 1, 1, 0, 0, 1. Noting that the last bit is a signed bit. Now, in terms of subtraction, let's have a minus b. If we are using unsigned code, so we're not talking about signed bit, all what we need to do is just add a to the 2's complement of b. Now, if the value of a is greater or equal to the value of b, we discard a carry, or we discard any carry that we might get. However, if a is smaller than b, then the answer is the negative of the 2's complement of the answer. Take, for example, this value, 1011 minus 1010. And this way, a equal to 1011 and b equal 1010. We get the 2's complement of b, and then we add a to the 2's complement of b. We get 1 as a carry and 0, 0, 0, 1 as the result. So the value is 1. And since a is greater than b, we discard the carry. So the value is 1. Now, if we flip a and b, this term, or this time, a is smaller than b. So, the first thing we do, we add a to the 2's complement of b. The 2's complement of b is 0, 1, 0, 1. A is 1, 0, 1, 0. Now we add a to the 2's complement of b, we get 1, 1, 1, 1. And since a is smaller than b, we have to have the 2's complement of the answer and place a minus sign in front of it. So the answer, as we said, is equal to minus the 2's complement of the answer, and that's the answer, 1, 1, 1, 1. The 2's complement is 0, 0, 1. And we place a minus sign at the beginning, and we get the result is minus 1. However, if we are using signed numbers, subtraction using signed numbers, it is basically normal addition. For example, if we want to subtract 5 from 12. 12 minus 5 is equal